All right, let's talk about something truly wild today. We're diving into one of the most extreme, most futuristic materials ever cooked up in a lab, aerogel. You might have heard it called frozen smoke, and for good reason. It is, quite literally, the lightest solid material on Earth.
I mean, just let that sink in for a second. This sounds like something straight out of science fiction, doesn't it? But it's real. We're talking about a solid object that looks like a captured cloud, is made of almost nothing but air, and has abilities that are just off the charts.
So, here's the big question we're tackling. Is aerogel really the S-tier wonder material of the future that's going to change everything? Or is it just an incredibly cool party trick? You know, a fragile, super expensive curiosity that's more like high-tech dust than a practical, world-changing material? That's what we're here to figure out.
And here's our game plan. First, we'll get into what this ghostly stuff actually is. Then, we'll trace its history from a simple lab bet all the way to outer space. After that, we'll unpack its frankly insane properties. Then, we'll get real about its uses, its costs, and its biggest flaws. And finally, we'll deliver the final verdict. Let's get to it.
First up, what is this stuff really? It looks like it might vanish if you blow on it, but it's a solid you can actually pick up and hold. Just very, very gently.
Okay, so here's the magic trick. You start with a gel. Think of something like Jell-O. Now, if you just let that dry out, it would shrivel up and collapse, right? But with aerogel, they use this incredible process called supercritical drying. It's a super fancy way of saying they gently coax all the liquid out without crushing the delicate structure inside. It's like trying to get all the water out of a sponge without squeezing it. All that liquid gets replaced with air, and what you're left with is just the solid skeleton of the original gel, a tiny tangled web of nanoparticles. And that process leads to this number, which is just mind-blowing. Up to 99.8%. That's how much of this solid object is literally just empty space. It's a material that's defined almost entirely by what's missing. And that nothingness is exactly what gives it its superpowers.
So, this impossible-sounding material obviously didn't just grow on a tree. Where did it come from? Well, its journey from a scientific bet to a hero of space exploration is a pretty fantastic story. It all started way back in 1931 when a scientist named Samuel Kistler made a bet with a friend that he could remove the liquid from a gel without making it shrink, and he won. But for decades, it was just this weird lab curiosity. It was difficult and kind of dangerous to make. And then, NASA came knocking. In the 90s, they needed something ridiculously lightweight to insulate the Mars rovers, and get this, a way to gently catch comet dust speeding through space. Aerogel was the perfect and maybe only answer. From there, things took off. We started seeing flexible aerogel blankets for industrial use, and now we're in an era of advanced carbon and graphene aerogels that are opening doors we didn't even know existed.
So that's the history. Now let's get to the really fun part, the science behind the magic. Just what makes engineers and scientists get so excited about this stuff? What can it actually do?
Let's start with density, or, well, the almost complete lack of it. Some versions of aerogel clock in at just 1,000th of a gram per cubic centimeter. To put that in perspective, that is actually less dense than the air around us. Yes, you heard that right. It's a solid object that can literally float on air. It's just wild.
And if that wasn't crazy enough, check this out. Because of that tangled microscopic internal structure we talked about, the surface area packed inside is gigantic. I'm talking up to 1,000 square meters from a single gram of the stuff. That's like taking a sugar cube and somehow unfolding it to cover a couple of basketball courts. It's a massive amount of surface area in a tiny, tiny package.
So let's put all of its superpowers together. It's got the lowest thermal conductivity of any solid, which makes it the best insulator on the planet, period. All those tiny pockets of air just stop heat in its tracks. Of course, being 99.8% air makes it unbelievably light, but don't let that fool you. It's shockingly strong, able to support 4,000 times its own weight. Add in that it can be made almost perfectly clear, and that new versions are hydrophobic, meaning they repel water, and you've got a combination of traits you just don't see in any other material. Okay, so it sounds like the perfect material, right? But this is where potential smacks right into reality. It's time for a reality check. Let's talk about where it's actually used today, and more importantly, what's holding it back.
So aerogel is definitely breaking out of its NASA-only niche.
Yes, it's still an absolute rock star for insulating spacecraft, but now we're seeing it in high-end building insulation, especially where you need maximum warmth in a thin profile. Its huge surface area is being explored for next-gen batteries and supercapacitors. It can even be used to soak up oil spills. And hey, you might even be wearing it. Some premium outdoor brands use Aerogel to make jackets that are insanely warm but not bulky at all.
But here's the fundamental trade-off, the heart of the issue. On one hand, you have Aerogel with thermal performance and low weight that is just in a league of its own. On the other, you have traditional stuff like foam or fiberglass. It's way cheaper, and it's durable. You can toss it around. You don't have to handle it with kid gloves. So you see the dilemma. With Aerogel, you get absolutely elite performance, but you're going to pay for it, both in cash and in hassle.
And that leads us right to its major weaknesses. Let's just lay them on the table. First and foremost, the cost is a huge barrier. And we're not talking a little more expensive. We're talking 10 times the price of normal insulation, or even more. Second, the pure silica form is incredibly brittle. It shatters like glass and can create a fine dust you really don't want to breathe in. And finally, just making the stuff on a massive industrial scale is still a huge challenge. It's a complex, energy-hungry process. These are the very real cracks in Aerogel's otherwise perfect facade.
So, we've seen the magic, and we've seen the messy reality. It's time to put it all together, weigh the pros and cons, and give Aerogel its final, merciless ranking. All right, here's the final scorecard. For historical impact, we're giving it a solid 7.5. It was absolutely critical for NASA, but its impact on everyday life is still pretty small. Now, mechanical properties, that's a huge 9.5. You just can't beat its insulation and low density. Workability gets a 7.0. The newer flexible blankets have made it a lot better, but it's still a fussy material. Scalability and cost, that's its Achilles heel, only a 6.0. The high price is still a major roadblock, but then we look at versatility and lasting relevance. We're scoring those high at 8.5 and 9.0 because its future potential in green tech and energy is absolutely enormous.
So you tally all that up, and that lands Aerogel firmly in the high A tier. It is an ultimate insulator, an irreplaceable specialist for jobs that demand extreme performance. But those very real issues with cost and fragility are what keep it from reaching that legendary, godlike S-tier status. For now.
And this really is the perfect way to think about it. Aerogel isn't a workhorse material like steel or concrete. It's a boundary pusher. It's a material that shows us the absolute limits of what's physically possible, redefining performance by being made of almost nothing at all. So I'll leave you with this thought to chew on. In a future that's going to be defined by our need for energy efficiency, for lightweighting everything, and for solving huge environmental challenges, how could a material that offers the ultimate insulation with virtually no weight not matter? Aerogel is proof that sometimes the most powerful solutions can be found in what looks like empty space.